Hi, today I'll be starting a new series, programming patterns, and I'll be starting with some basic dynamic programming. A lot of people, including myself, commonly struggle with dynamic programming, and how to get started. And I'm hoping that this series will help kind of make it seem not as intimidating as it could be. By identifying some common problems. We'll cover four in this video, and then seeing what ties them together, and how you can basically use knowledge from one of these problems and kind of extend it, without using that much effort into thinking of like a very novel solution. And a couple of disclaimers. The dynamic programming I'll mostly be explaining is going to be bottom-up dynamic programming. I think a lot of people would have kind of trouble, or it would be easier for people to do top-down because you would just do the recursive solution and memorize it. And so I'm not saying bottom-up is like a lot harder, but it's just not as intuitive if you already know like the brute force recursive solution, which I assume is like I'd say is a prerequisite to even getting started to learn dynamic programming. And with that said, without a lot of the way, let's get started with our first problem, the longest increasing subsequence. So given an array of nums, return the length of the longest strictly increasing subsequence. Okay, so let's tackle this by bringing up the good old trusty notepad. So as you can see, I already put the sample case here, and I've already initialized a DP array. And so if you think about this, we initialize the DP array with ones. And this is because in the beginning, every number itself is a subsequence, and it's of length one. And so since a number is by itself, it is strictly increasing. And so every one of them is default length one. And so how do we do the state transition? Well, it's easy. Let's start looking at all pairs of numbers. So just a simple, n squared loop, looping through all pairs of numbers. Of course, starting with the second element. So let's look at the second element versus, if we start here, let's take a look at here first. I'll draw this using the triangle instead. So if the current element you're on is greater than the element you're looking at, the other part of the pair, then you can increase it by one. You can increase the DP array state by one. So in this case, let's just get to a better place. So if you think about it, this is not increasing. And then if we move on to two, this is not increasing, this is not increasing. So let's move on to five. This is obviously not increasing, this is not increasing. And so, but here we have an increasing, right? So five, we can append that to the end of the subsequence that ends in two. And so now we can just basically say, so what's the length of the subsequence of two? Well, we can see it, we can get that from the DP array, which is one. And then all we have to do is to add one to that. So let's go ahead and change that so that now it's two. Oh boy. There we go. Two. Now we move on to three. Again, we go here. Nope. Nope. Yes, this is increasing. So this is two. And of course, if the well, you'll see later. But all right, now we move on to seven. Seven, there's no. Yes, this is increasing. So now we get two. Because 1 plus 1. But then 7 and 5, that's also increasing, right? And so we get another subsequence that goes 2, 5, 7 instead of just 2, 7. And this gives us actually 2 plus 1, which is 3. So instead of always just setting this, we take the maximum, which is of the current options we've explored. And so we move on to 7 and 3. And again, this is also 3 because we can go 2, 3, 7. So it stays at 3. And then finally, we move on to 101, which in this case is 4, because it can go out to 7, 18, which is also 4. Okay. And so at this point, we have this DP array of the longest increasing, or the LIS ending at every element. And all we have to do is to find the maximum of this array. All right. So if you want to see implementation, I will quickly bring that up. But it's a rather simple double nested for loop. And then just a quick check to see if it is less than, if it is, then we take the max of either itself or the element -1 or +1. And then at the end, we return the max of the DP array. All right. Let's go ahead and make a new one. This brings us to our second problem, coin change. You are given an integer array coins representing different dimensions and an integer amount representing a total amount of money. Fewest number of coins that you need to make up that amount. Well, let's think about it this way. Okay. So let's use this example of 1, 2, and 5. First of all, we want to, again, let's use the idea from the previous one, right? We can think about this 11 as kind of like sequences, just like last time. So let's make a DP array that represents 11. And so at index 0, or this will actually be amount +1 because we're going from 0 to 11. So we actually a length 12. So let's think about why, or I'll explain why as we move on. So in the beginning, we have 0, right? So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. All right, 0, and then basically infinity for every single element. Okay. And so what does this mean? Well, if you don't have any coins, then all you can do is 0, and you cannot make any of these amounts. So that's why we put them as infinite, basically representing that we can't do that. And so what we can do is to kind of introduce the coins one by one until we get a good answer. Okay, so we have an infinite number of each kind of coin. So in 1, 2, and 5, right? So let's start out with 1 because it's the first element in the list. And so, well, how many coins does it take to get from 1 to 1? I mean, well, it's the same amount of coins to get to 0, which is 0, plus 1 because we have that 1 coin, right? And then same with 2, 3, 4, 5, and so on. So let me just all of these infinities basically get turned all of these 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, right? Because the number of ways to get to 1, well, it's just 1 more than number of ways to get to 0 because we're having a 1 cent coin. Then 2 is 1 more than 1, 3, 4, and so on. So you get the idea here. And then moving on to 2, right? So how can we get from 2, or how to get, well, we obviously can't get to 1, right? Because 2 starts at 2. So we'll start at 2. So how many coins does it take to get to 2? Well, currently we have 2, right? Which is made of 2 1s. Or since now we have 2, we can do -2, right? Or we can look at the elements 2 over, and then that's just +1, right? Because we are adding one $2 coin or 2-cent coin into the total sum. So we can either do 2 or 1. And so which one should we pick? Well, what does it say? It says the integer amount or the fewest number of coins. So in this case, we'll take the minimum of 2 and 1, which turns out to be 1. Okay, and then we repeat this case with 3. So we can either do 1 and then or we can do the current 3, which is just 3 ones, or we can do a 1 plus a 2, right? So that would only take 2 coins. So this 3 would get made into 2, and then so on and so forth. And then we can work our way up until the end of the array. So again, this can be very easily accomplished with a double for loop. And this will, or here's the implementation. And then you start it off with infinite, and then as you go on, you take the minimum of either what you have, or the number of ways to get from I minus C plus 1, because you're adding C amount. All right, wasn't that hard, was it? So you're given a insecure number of coins or array of coins again, and it says number of combinations that make up that amount. And so stop doing that. Okay. And so again, the same idea, right? This time it's a more reasonable example of 5. So let's make a array representing 5 again. All right. So this is going to be our DP array, and we are going to initialize them with, again, or the same similar concept, except it's kind of flipped this time. So we know that there's one way to get 0, right? I don't have any coins, I'm at 0, and that's one way. And then for now, we think that the rest of these we can't get to. There's no way to get to any of these because I don't have any coins. The only coin the lack of coins makes me be able to hit 0. So again, we can go ahead and add them in one at a time. All right, so let's start with 1. How many ways are there to get combination of 1? Well, that's just the same as the old one, right? Because we can get to 0 one time. Now we can get to 1 the same amount of times by just adding 1, right? And then how many times or how many combinations does it get to 2? Well, it takes we have a 1 coin, and we know that it takes 1. It's a 1 combination to get to 1. So just adding that just makes it another combination. So now eventually, once this is all over, as you can see the pattern goes, we get to all 1s. There's one way to make 0, and since we have 1 coin, we get one more way to making 1, get another way of making 2, and so on. All right, so we're done with that. Now let's look at 2. So, or first of all, we know we can't reach 1 with 2, so we'll start over here, just like last time. And then how many ways are there to get to 2? Well, we know there's one way to get to 0. And then we already have the one way from before, which is 1 plus 1. So we get an additional way, which is just 0 plus 2, right? And that's one extra way combination. And so in this case, now we can essentially turn it to 2. And then from there, we know that this gets turned to 2, this gets turned to 2, and this gets turned to 2. All right. Finally, we'll work with 5. We know, oh, actually, I was actually wrong there. This gets turned to 2, right? But then when we're at 4, we can do, there's 2 ways to get to 2. And we already have one way of getting to 4. And so there's 2 ways here, and that essentially translates here because we got 2 plus 2 is 4, right? That just gives us 2 more ways to get to 4, which means it's actually 3 here. And in the same vein, this is 3. So now we're done with 2. Finally, at 5, we start at 5. How many ways are there to get to 5? Well, just from 0 to 5, which is 1 more way, right? We go from 1 here, we get 1 more way compared to everything we've done before. So this is now 4. So the answer would just be the how many ways, or the last element in the DP array. And again, here's the implementation. A DP array, some 4, it takes 1, and then we can see that we're just adding the number of ways from I minus C. All right, partition equals subset sum. So given an integer nums, return true if you can partition the array into 2 subsets such that the sum of the elements in both subsets is equal, or false otherwise. So at first glance, you could think that, this is no relation to the other 3 problems that we were talking about. This sounds like, a constructive, like how to construct, like just, how many ways are there to either go choose 1 in one set and 1 in the other. But the trick is to remember that if we can partition the array into 2 subsets, such that the sum is equal, well, what's the sum of each subset, right? Each subset is going to have the total sum divided by 2. All right. So again, this only works if it's even. If the total sum is even. If the total sum is odd, we immediately know that there's no possible way. And so only if we find total is 2. So what does this sound like? Well, it sounds kind of like coin change, doesn't it? It sounds like coin change that we're looking for, the value we're looking for is total over 2. Well, but there is one big difference from this to coin change. In this case, we can only use the array elements once. Remember in coin change that it was assumed that we have an infinite number of coins. And so how do we deal with this? Well, remember what we did in coin change, right? So especially remember the ones, right? The 1 coin. So for example, if we had something like this, right? Or the 1 and 2, let's say. First of all, these zeros would all turn into 1s, right? From the 1. And then from 2, we know that we can create 2 from here, 0, the 2, or 1 plus 1. But we don't have that luxury of 1 plus 1 anymore. And so really in this case, it should have just been the first 0 that has turned into 1. But in the way we're iterating through our for loop, we're iterating this way, right? So anything that we encounter, it might have a chance that we've already encountered, like we've already set for. So if we're going to here and we're looking 1 behind, we've already set this 1. So of course it's going to be 1. So this is going to be 1 also, but we don't want that. So how do we fix it? Well, I think I might have given it away when I was talking about the for loop, but let's think about it going this way. So we're still checking to see the previous one, right? And only if the previous one is, a 1, then let's change it to a 1. Right? Otherwise, just change it, just keep it as is. So this will stay a 0. We'll look here. This will stay a 0. Then we'll look here. Still stay a 0. And then we'll look here. Oh, there's a 1. And now we know that it could be a 1. And so, again, these are going to be true or false values. So to make it easier, and then we can basically apply the same logic. So with 2, right? We can start here, we can look back 2, and oh, we can make 2 here. And then we can start here, look back 2. Oh, well, 2 is possible here, right? And so this is either, 0 plus 2 or 1 plus 2. All right, so, and then in the end, our answer is just going to be in the last element, whether it's true or false. All right, so let's see what this code looks like. So we find the total. First of all, check to see if it's even. If not, then we can just immediately return false. Otherwise, we divide it by 2, and that's going to be our target. And so if we get to target, again, do the target plus 1, set the first one at true. We could do our double for loop again, and then do an or, basically, to see if it's, if it is true, then it can also reach the next one, and then we do return the last. All right, and that concludes the videos. This is it. I think this is a more experimental video, and my explanations might not have been all that clear, or you might have not associated all these together. But if you look at the solutions for each one of these, they look oddly familiar. Right? The signature, like double for loop. So okay, so double for loops would also apply for to a 2D array, right? But in this case, it's just going to be a 1D DP array that you can just use a double for loop for each of these. And so what I wanted to accomplish with the video is kind of, if you encounter a new problem, kind of like this, so I've actually got my inspiration of solving this partition equal subset sum from just coin change, right? As long as you figure out the trick that if you get to target over 2, then that you can divide it into 2 subsets. And so the goal is to just get the understanding, and hopefully if you encounter any problems similar to this, you would at least think of this as an idea. A couple of things that I didn't mention while I was going over through is that the coin change here. So you might think, or you may encounter the problem where it says instead of the number of combinations, it would be the number of just the number of different ways. So instead of combinations here, it can be permutations. So for example, if it's just 2 plus 2 plus 1, you can also do 1 plus 2 plus 2, or 2 plus 1 plus 2. So the trick to that one is actually relatively simple. You switch the order of these for loops. That's right. So except of course start this at 0 and do an extra check for out of bounds. So why do you switch the 2 for loops? Well, because if this is on the outside, we're iterating through the amount, and we're always iterating through every coin. You can think about it this way. Because we're setting this for loop out here, we are basically setting an order for the coins. So because we're setting an order, we ensure that the coins are encountered in such a way that it's the order in the list. So for example, here you can never get to 1 plus or 2 plus 1 plus 1 plus 1 like this, right? Or even though it says it in the comment, but in our code, it's always just going to be 1 plus 1 plus 1 plus 2, right? Because we're kind of fixing the order, and that's why we can get away with just doing this for combinations. But for permutations, we can just flip it, and then we wouldn't be fixing the order anymore. And then just another quick side note for the longest increasing subsequence, I am aware of the n log n solution, but I think for an introduction and for the purposes of this video, it's, and again, even this code passes. This code even passes because the constraints are good enough. So an n squared solution works fine. Okay, that's all for me. I hope you enjoyed, and have a good day.